So, unlike previous questions I've been asking about graphs, where we're trying to model a specific problem and come up with a graph with what properties for that specific problem, I want to change focus and I want to start talking about abstract problems. So, the problems we're going to be talking about today are not ones that necessarily only apply to one particular graph, but you can imagine applying to any type of graph. And you could use these general algorithms or these general problems as a way of framing any particular problem you're trying to work on right now, say that semantic scholar thing. So this first type of generic problem I want to introduce is this thing called the ST connectivity problem. So what is this thing? The idea is you're given a source vertex S and a target vertex T. The question is, does there exist a path between S and T in the graph? And again, remember, this is abstract. This graph could represent anything. So we're just asking, are S and T connected? Now, you could probably easily do this by just looking at it. In this graph, S and T are obviously connected. There is a connection between them. You could do something like go from 0 to 1, and 1 to 4, and 4 to 5, 5 to 6, 6 to 7. Those two nodes are connected. Now, what we're going to see is a little bit tricky is, how do you describe that process that you use with your eyes to something that is as stupid as a computer, that doesn't understand how to look at things? How do we describe the process to work for any graph of any size with any number of edges or formats to tell if two nodes are connected? So we want to try to come up with an algorithm for this that describes how to go about this for any graph. So there's a clever insight here for how we're going to develop this algorithm, that this task is in some sense self-repeating. What I mean by that, so if we think back to when we outlined this path in our head, going from 0 to 1, 1 to 4, 4 to 5, 5 to 6, 6 to 7, remember the question we're trying to answer is, are these two nodes connected? Is there a path from S to T? And so you can actually break this problem down into somewhat smaller versions of that problem. So for example, if you want to figure out if 0 and 7 are connected, well, that's the same as asking, are 1 and 7 connected? And there's an edge from 0 to 1, right? So if you knew how to solve the 1-7 connectivity problem in this example, then you could solve the 0-7 connectivity problem because there's an edge from 0 to 1. So we're going to see that this algorithm that we're going to come up with is actually going to use itself as a subroutine. Ask the question, are these two nodes connected? And hopefully making progress on that graph. Whenever you hear this idea of a subroutine or a self-similar task, that should maybe start ringing the bells of, this is a recursive structure, solving the problem in terms of a smaller instance of itself. So I've written up some pseudocode to describe this process. So the connected problem between S and T, well, if S and T are the same, like if we're at the same node, well, then they're going to be connected, right? If I asked, are 7 and 7 connected? We can say by definition they're the same node. We'll just say that's true. Otherwise, suppose I'm starting at some node S being 0 and at my target is this node T. Well, the first thing I do is I'm going to loop over all of S's neighbors. So I'm going to say, suppose I have some kind of notion of neighbors. Oh, one thing I should mention is in this pseudocode here, it's pseudocode. So we're going to assume that there is some way, the structure we're providing, to say, hey, it's really easy to find the neighbors of a particular node. I'm not writing the exact Java statement you would have to write to figure that out, but it describes the computation that's necessary. It describes find all the neighbors in whatever representation of the graph we're using. So for each vertex in the neighbors of our start node, we're going to ask, is that neighbor connected with our destination, T? And if it is, return true, otherwise return false. But asking, are N and T connected is not necessarily an easy problem, because that is going to have to call this function again. Well, is the node 1 the same as the node T? No, so we have to go in the else case. Then we have to say, okay, for each of this node's neighbors, 2 and 4, try calling connected on them. And if you remember with these kind of structures where you have looping and recursion, remember when you recurse, you kind of pause and go run all of that code before coming back and continuing. So it's going to go ahead and say, suppose it chose 2 as the next neighbor. It's going to go and run connected 2 and 7 all the way through before coming back and then trying connected 4 and 7. So we actually, so this is kind of a description of this algorithm. And so you already might be thinking, Hunter, I'm not so sure about this. This seems a little sus. I want you to play with this for a second. Let's think about this algorithm and if this is going to work on this graph or if it's guaranteed to work on all graphs. So take a second. Will this solution that I just described always work? Open-ended question. Try this out for yourself. Is this the right algorithm? Okay, so hopefully you had some time to think about that. So I would argue that this algorithm, as I described, even though it's kind of nice, it's not the most intuitive with this whole recursion thing, but it's kind of this nice description of just go to a node, visit all of its neighbors, have them visit all of their neighbors, and so on until you find the destination. However, the way I described it, this isn't guaranteed to work. So let's think of a trace, an example of this. So for example, suppose we're starting with this 0-7 connectivity problem. And I say, okay, well, I need to enter the else case because 0 is not the same as 7. Go to all of its neighbors. So I'm going to start with the first neighbor, say it's 1. So I'm going to ask, is 1 connected to 7? So I make a recursive call. And in that recursive call, I say something like, well, okay, well, is in this node here 1, is 1 the same as 7? No. So go into the else branch. For each of 1's neighbors, make this recursive call. Now, suppose the first neighbor returned is 0. Well, then if it returns 0, then we're going to call connected on 0 and 7. Oh, how do I figure out if 0 and 7 are connected? Well, I need to, whoops, that didn't change colors. To figure out if 0 and 7 are connected, I need to ask, are 0 and 7 the same? No, so I need to go in the else case, go to all of 0's neighbors, and you can get caught in this back and forth forever. Going from 0 to 1, back to 0, back to 1, back to 0, back to 1, back to 0, and so on and so on. In our description of this algorithm, there was no guarantee on the order that you're going to visit your neighbors. So it's not guaranteed to you that you will go explore a new path. You might just go back to where you were before. And even if you could try to come up with clever orderings, I would still argue that this would still be hard, because what if you have a cycle? It's really hard for you to tell kind of if this is new territory or not. So almost any graph traversal algorithm, what we just described here was an algorithm to go through a graph. Almost any graph traversal algorithm we'll come up with is going to need some extra information it needs to keep track of. They're going to need to keep track of, where have I been? Which nodes have I already visited so I know not to explore those options? In terms of the code, it tends to show up in one very common way, which is to just keep track of which nodes you've already visited. So keep track of a set of vertices, called it visited, and just to keep my code on the slide simple, we're just going to assume it's like a field or a global variable, but you could also just pass this around as another parameter into your recursive calls. So all we're going to do is keep track of this visited set, and then every time we visit a new node, we add it to the visited set, and whenever we're looking at a neighbor, we only explore that neighbor if we haven't yet visited. So the way this algorithm will now run is we're kind of starting at 0, and then we say, okay, well, I haven't visited 0 yet, so I'm going to add it to my visited set. So maybe I'm just going to draw this as like a little check mark next to it that we have visited it. And then we're going to go to all of its neighbors and say, oh, okay, well, what are all the neighbors here? The first one is 1. I'm going to ask, has 1 been visited? No. So make a recursive call. And then we say, okay, we'll go into the else branch because it's not the destination, add it to our visited set, check it off, then go to all of its neighbors. So maybe start with 0 and say, well, I'm not going to enter this if statement here because visited contains 0. So we'll just skip it. Never go back to never look back, essentially. Just only go to something new. So on our next iteration, maybe we go to the 2, then we make a recursive call because 2 is not in our set. So we can then add it later and we keep exploring in this way. So this approach of just adding a set of visited nodes is like the super common strategy for almost any algorithm that has to iterate over nodes in a graph. So what we have just described here is this traversal algorithm called depth first search, or DFS. So why do we call it depth first search? Well, it's a little tricky to think about at first, but there's a very particular way in which we're visiting all the nodes in the graph. We're not trying to make a statement about what order you visit all your neighbors. We're going to assume that your neighbors return a set in some arbitrary order. But if you think about the flow of the whole graph, there's a very particular way this algorithm, as described, does this. In some sense, what it's going to do is when you go to explore your neighbor, you're going to go all the way down that path before coming back to any other option. Now, what do I mean by that? So suppose in this graph, I'm asking, are 1 and 3 connected? So I'm trying to see, is there a connection between 1 and 3? So let's simulate what this algorithm does. It starts at 1. That's not our destination, so we go into this else branch. We add 1 to our visited set, so we mark it as visited. And then we say for each of its neighbors, well, let's suppose we start with 2, and then we ask, well, is 2 in our visited set? Let me pull up my drawing tool so we ask, is 2 in our set? No. So we're going to make a recursive call on that. So then we kind of come back at the top and we say, oh, well, is 2 the same as 7? Or sorry, is 2 the same as 3? No. So we're going to add it to our visited set. And then we're going to iterate over all of its neighbors. So for example, that might start with 5. Then 5, we kind of ask, well, that we need to visit all of its neighbors. So we added 5 to our visited set, iterate over its neighbors. Maybe we go to 6. Then we go to 9. And then we can come back once there's nothing left to explore. We undo the recursive call. We kind of left off where 6 was. We were waiting for 9 to tell us if they're connected. They said no. So go on to my next neighbor. So go on to 7. Oh, nothing's there. So exit back. The 5 will end up checking its next neighbor. Then the 1 will check the 4, which will check the 3. Notice we kind of made a wrong turn in some sense, where we first started looking at the 2 and we had to explore that entire part of the graph before coming back and exploring that next set of nodes. This is why we call this depth first search. This happens because when you have these recursive calls, you're pausing the program and going to go run everything else there. And so before you're able to explore all of your neighbors, you have to go down this whole path. And so we're going to talk about in our next video some algorithms that try to take a slightly different approach. But this algorithm we're going to call depth first search. I want to quickly highlight one thing about depth first search, though. This is something you're slightly familiar with already, but not by name. So if you think back to tree traversals from 143, these like pre-order, in-order, post-order traversals, just going through a tree and then going through it, all of these traversals ended up being depth-first searches. Now, what we mean by that is you started a node, and then you explore its left child and explore that entire subtree before coming back and exploring the right subtree. These are all the properties of depth-first search, where you kind of go all the way down one path before coming back and trying another. It turns out it doesn't actually matter in the case of thinking about these searches of doing a pre versus in versus post order traversal. That's just all about how you handle yourself with respect to your left and right children. But that doesn't change the fact that you first go all the way down the left tree, come back before going down all the way the right tree. Same thing when we talked about exhaustive search or recursive backtracking. We exhaustively tried all of the options down one path before coming back. So whenever you see this kind of exhaustive search strategy, like phrased in this recursive way, we're going to almost always be in this kind of depth first search approach. But in our next video, we're going to propose an alternative.